Today we're going to talk about the reimplementation of RouteNet-Fermi network modeling with graph neural networks with our group members Shurya, Simran, Swati, Arpan, and Ishan. So let's get into the topic. So modern networks, as we know, are complex with dynamic traffic patterns and diverse protocols, and networks quickly increase in scale and complexity. So we need to optimize the model and optimize and we can do this by predicting network performance metrics such as bandwidth, latency, jitter, and packet loss. And this is crucial for optimizing real-time applications. And so some traditional network performance models include queuing theory models, which assume Markovian traffic, which is extremely inaccurate in real-world network dynamics. And network simulators have extremely high computational costs for large-scale networks, but they're extremely accurate. So to fix both these problems, this paper aims to use graph neural networks. And the way they do this is that the input to the model is the topology, the routing configuration, scheduling configuration, and traffic model as well. And then that's fed into the graph neural network model. And then they measure the performance metrics, including the delay, jitter, and loss. So the graph neural network models the relationship between nodes, which are the routers, and edges, which are the links. So this network topology is fed into the graph neural network. And this graph neural network has many different phases. So it has an initialization phase, a message passing phase, and a readout phase. So they use a simulation framework for different network topologies using OmNet++, which is a discrete event simulator, and they use this to calculate delay and set of source destination flows, generating use the power law out degree algorithm, which means that there are very few number of nodes with which a large amount of outgoing edges, and the traffic distribution follows a Poisson process. So they vary many different variables, including the different topologies, the traffic models, the traffic intensity, and queuing configurations. And within the graph neural network model, they implement three different types of cells: RNN cells, LSTM cells, and GRU cells. So within the paper, they only implement GRU, but we tried other cells like LSTM and RNN. So RNN is a simple recurrent cell, which is a more simpler version of GRU, and it updates the hidden state each time step, but it struggles with long-term dependencies. But the benefit of GRUs is it has a reset and update gate within the GRU, which controls the flow of information, handling medium-term dependencies. But why we think the LSTM will be better is because it has a forget input and output gate, which helps maintain how much information is kept within the hidden state.
Yeah, and looking at the results, we can see for the fat tree topology data set, we tried three different topologies with 16, 64, and 128 nodes. And for all of them, we can see that the RNN model performed the worst. However, the LSTM model performed the best for fat tree 16, and the GRU and LSTM had comparable performance as compared to the paper as well. For the real traces of traffic topology dataset, it models the topologies more like how the real world works, and it had a 24 node topology with 26 variations of shortest path. And we can see that the paper GRU model performs the worst, and RNN is close second. LSTM, however, performs the best. For the scalability data, it had more nodes. It had 50 nodes per topology, and while measuring the delay of the packets and the jitter of the packets, the performance were comparable. However, the RNN model in the scalability jitter prediction performed much better, surprisingly. For the scheduling policy data topology datasets, we had 24 node topology, and it used strict priority scheduling and weighted fair queuing. And for predicting delay, jitter, and packet losses, all of them showed that the RNN model performed the worst, and the LSTM and GRU models had a comparable performance. And we also compared to the paper GRU, which also was pretty close. Finally, for the traffic models, it had 100 variations of shortest path of the nodes within the topology and 24 nodes for each topology. And it had 5 different subtasks as well, which included constant bitrate, on and off, autocorrelated, modulated, and all multiplexed. And for all of them, we can see that the RNN model performs the worst and the LSTM model performs the best. However, LSTM and GNN are still very close in comparison. I also wanted to share how the training validation loss looks because the RNN models were performing really bad. We wanted to see why that's happening, and you can see that the RNN is slower to converge while training, while the GRU and LSTM have close performances. The training time for all of these experiments was around 6 to 24 hours per training run, and we performed around 72 experiments in total. We could not fit all of them in here, but all of them are in the report. Looking at the inference time, we can see that when we increase the number of nodes in the topology, the inference time for the model increases as well. We tested from 10 to 300 node topologies, and around 150 node size, the inference time goes from 2 seconds to 3 seconds. So in conclusion, network modeling usually has traditional methods which are computationally expensive, and RouteNet-Fermi uses graph neural networks to predict network performance like delay, jitter, and packet losses. And they only implemented the GRU model. However, we re-implemented the GRU model and extended it with RNN and LSTM models and saw that the LSTM model had the best performance. Thanks for listening. The open source code is available on GitHub. You can go through it using this QR code.